If that's the case, then your goal is only to continue believing in a spinning globe or continue believing in Santa Claus. I think he's due. At any rate, using Stellarium, it's an astronomical software. I was able to document multiple constellations first during the evening of December 24th, 2015, both north and south, about 60 degrees from the horizon, mean. I spot checked multiple constellations over the course of that evening. So, again, the first night I checked was December 24th, 2015, just to sort of jot down some of the constellations and stars that I could see that evening. I would have included the entire process as a video. However, for some reason I couldn't screen capture that software, so it just came out as a blank nothing. So I just had to film my screen as sort of an example and use documentation and screenshots for the rest. But anybody can replicate this. It's fairly simple to do. Um, then I did the same thing on June 24th, 2016, so 6 months from now, and just sort of spot checked a bunch of random constellations and stars throughout the evening. First facing north and up and documenting stars that way, and then facing south and up, and just sort of documented a bunch of different constellations and stars throughout the course of the evening, looking north and south on June 24th, 2016. And again, the first day was December 24th, 2015. And suffice to say, I was not surprised to find that most of the star constellations are visible during the summer and the winter. I documented my findings in a quick review of the spreadsheet, so I'll just roll that clip. Okay, so what I did was took Stellarium and just played around with it for a little bit. Pretty easy to use once you mess around with it a bit, get the hang of it. And I just, spot checked, randomly noted some stars and constellations and different patterns and such in the night sky facing north in December. So, like yesterday, December 24th, 2015, facing north and just watching the stars sort of pass by in the night sky in time lapse version. So, just noted some of them: Andromeda, Arcturus, Auriga, Bootes, Chemily, Pardalis, Cancer, Canis, Venacci. So I'm not going to list them all, but I will sort of scroll through them and show you that I documented not all of the stars that were visible in the night sky during that period, but I did it facing sort of like north and then looking up into the sky, and just sort of documented a bunch of those throughout the evening and put them in alphabetical order. There's no order to these, but alphabetical. And then did the same thing on the same day facing south. And of course, there were some of the same stars from north to south, but just sort of getting an idea of what sort of stars we can see at nighttime on December 24th. So that'd be, winter for sure. And then I did the same thing, fast forward 6 months to June 24th, and faced north and just sort of took note of, there's a duplicate, oh well, took note of all the different stars I could see throughout the evening facing north and then again facing south. So, what I wanted to do was just see if I could see any of the same stars from winter to summer, because people argue that you can't. People argue that there are constellations that are unique to the winter and summer, and so therefore the Jeranism effect, or the fact that the sector of space during the winter in the heliocentric model would be the opposite end of the universe, totally invisible because of the sun for the entire summer, so the opposite 6 months of the year. And basically, what I found was, yeah, there seemed to be some star patterns, or maybe not, but there seem to be some that are exclusive to winter or summer. But on the other hand, most of the same stars and constellations that you can see in the summer, you can also see during the winter. So, if you can, hopefully this records, but the left-hand side is all of the stars that I documented, and it certainly isn't all of the stars, just sort of ones that I randomly spot checked facing north and facing south during the evening of December 24th, 2015. And those are in blue down the left. and the ones from 6 months from now or 6 months later from June 24th, 2016 are on the right, sort of in orange or pink. And what I did was is I highlighted the stars or clusters or configurations, constellations that are not unique, so that are visible in the winter and in the summer. And again, it's most of them. And these aren't even all of them. These are just the ones that I happen to spot check. So Andromeda, Andromeda, Aquarius, Aquarius, Aquila, Aquila, Auriga, Auriga, Booties, Booties, Cancer, Cancer, Canes, Venatici, Canes, Venatici. It goes on and on. Capricornus, Cassiopeia, Cepheus, Coma Berenices, Corona Borealis, Corvus, Crater Cygnus, Lacerta, Leo, Leo Minor, Lepus or Lupus. I either misspelled it or maybe that's not one, but I guess it's either Lepus or Lupus. Libra, Lyra, Ophiuchus. Sorry, I don't know all my stars and constellations names. Pegasus, Perseus, Pisces. All of these are common to winter and summer. Uh, Piscis austrindis, Sagitta. It just goes on and on. I mean, it's Serpens, Sextans, Triangulum, Ursa Minor, Ursa Major, Vega, Virgo, Volk, Pecula. And so anyway, this demonstration, and I'll try to generate this as a PDF as well and just sort of let you look at all of it at once because there is a lot of data, and I'll put an example of sort of how I did this with Stellarium. But hopefully this will prove to you guys that the heliocentric model is wrong, simply because we can see many common stars from winter to summer, which would be totally impossible in the heliocentric model. Another observation that makes absolutely no sense whatsoever in the heliocentric model is the total lack of parallax or stellar parallax. What I've done in this little experiment here is pretty simple. I basically fixed a little piece of trash to my window screen and filming out through the window screen at objects in the distance in relation to the object nearby, which is the piece of trash in my window screen. It actually looks like a pretty good UFO, doesn't it, if you get the angles right? Oh, it's a UFO. Anyway, no, it's just a piece of trash, but if you notice that when just simply turning the camera from side to side, I'm not moving, I'm only just pivoting, so the angle of my field of view is changing back and forth. You'll see that the very near object, the piece of trash stuck to my window screen, is moving at a much more apparently faster rate as compared to the trees in the background. And furthermore, the trees in the background are sort of sliding along at a faster rate than the objects in the far distance. But you can definitely tell that the object in the near is moving at a much faster apparent speed than the objects in the distance. And this is a major issue with heliocentrism. According to the mainstream narrative, the closest star is about 4 or 5 light years away, which is extremely distant. 4 or 5 light years is just astronomical. However, the most distant visible star with the naked eye is allegedly say between 1,500 and 3,000 light years away. So I'll just say around 2,000 light years away, but this is all, of course, just theoretical. And of course, you're going to have stars just about every distance in between in all directions. And so the fact that we allegedly spin around in space and we don't see any sort of stellar parallax whatsoever, you should see major stellar parallax all over the place, especially year to year, season to season. There is no stellar parallax, so this conclusively debunks heliocentrism alone, just that one point. I wanted to dive a little deeper in the Arctic midnight sun phenomenon really quick. I made a video about this a few days ago. This was originally pointed out by Mr. Thrive and Survive, and he credited OD Picu, if I'm saying that right. And I had originally thanked you guys in that video I originally made, but I had to cut it back to 15 minutes, and so I did put a little props in the descripts, but I'm just going to do probably a double make this 2 15-minute videos, so I'll keep this in here. But anyway, okay, instead of just having a simple spinning circle, I decided to add some data points on the animation to make it a little bit more complex, get a little bit more data out of it, and get a little bit better sense of how we'd experience the midnight sun from the Arctic if we lived on a globe. So if you just watch the second animation on a loop, it shows how an observer might experience the summer midnight sun in the North Arctic Circle. One thing you'll notice is that the footage shows, or the real footage shows, the time-lapse camera going in a nearly perfect circle over the course of the video. Now, in terms of speed, tracking the sun here is a perfectly timed circle. So he's going around in a consistent speed and keeping the sun directly in frame, not up and down, but in the center of the frame, going around in a consistent speed. And again, the sun sort of sinks and raises over the course of the day, but the rate of travel is perfect. Also, the scenery surrounding the observer is going in a perfect apparent circle around him. If you compare this with the diagram animation here, the path of the sun would be wildly different than what we experience in reality. The scenery around the observer would change in wild, conflicting directions throughout the course of the day, as the sun would remain fixed, essentially, but the observer would be spinning on a tilted saucer of sorts. After considering this diagram and viewing the actual footage of the Arctic midnight sun, do you think it's a good representation of what you'd expect to see on a spinning saucer tilted towards the sun? Watch the points within the Arctic Circle and their relationship with the observer's line of sight, and how that line of sight changes angles between points within the Arctic Circle and points outside of the Arctic Circle. So, in order to get the observation that we actually get in reality, the Earth must be stationary, with the sun going around overhead. In reality, the observer on a globe should maintain his angle towards the sun for 6 hours, then modify that angle over the course of the next 6 hours. Then, during the next 6 hours, he would maintain the angle, and for the final 6 hours, say morning through noon towards the evening, he would constantly modify the angle to follow the sun.